Byron at University of Washington, and he directs the Robot Learning Lab. So Byron has straddled, many different fields, and there's this big debate in robotics about designing systems and designing algorithms. I think Byron has done both of them and done them really well. It's reflected in the 12 Best Paper Awards that his work has won. And interestingly, some of his Best Paper Awards come from machine learning venues, like ICML and AI stats, and other come from robotics. It's a very unusual combination to do, such good work in both the disciplines. And, if you read, Byron's description of his research, he also talks about quantum physics using non-parametric statistics, optimal control, and reinforcement learning. It's as interdisciplinary as it can get, right? Robotics is a system, and I think Byron's research is at the full stack. So we are very excited, Byron, to have you. And the side note, I think the notes on reinforcement learning have been very helpful. Both in catching up, but also when I was making my class, I used to refer to them. So thank you, for posting those notes. With that, let's welcome Byron once again. And Byron, looking forward to your talk. Please take it away.
All right, thank you very much for the lovely introduction. So I want to get started by talking a little bit about just a little bit of sort of biographical stuff. As Pulkit mentioned, I've done work in machine learning and sort of more increasingly have been focused on robotics. And you all have kind of caught me at a pretty interesting time in my career. So in 2019, I moved here to the University of Washington from Georgia Tech. I got tenure, and then COVID hit. And so like all of these things together made me sort of step back and think a little bit about what I really wanted to work on with this newfound post-tenure freedom. And so I decided that I didn't really want to work on boring robots anymore. And what I mean by that is simple robots which are moving slowly in indoor environments. And I guess I was kind of thinking back to when I was a kid and the types of awesome robots that I imagined I might be working on someday. And so with that in mind, in the last few years, I've really been focusing on what I like to think of as aggressive, meaning not conservative, robotic systems. So these are dynamic robots that are interacting with complex environments. Okay, so I'm about to show you a few videos. Let me know if they look smooth or if they're super choppy. This idea of working on aggressive robots came out of some of the work that I was doing at Georgia Tech on 1/5 scale cars that were racing around dirt tracks. So here we have a video. Is this video smooth or choppy? What do you guys think?
Pretty smooth.
Great. Okay. So if you look at the dynamics of this vehicle, they're really hard to model, right? So the vehicle is bouncing and sliding as it goes around that turn. And what we did is we used fast model predictive control with simple models. So sort of constantly receiving feedback from the environment about the vehicle's attitude, and then allowed the vehicle to adjust its actions as it experienced perturbations. And this allowed us to adapt a very aggressive racing strategy. So more recently, we've been using MPC to control 7 degrees of freedom robot arms. So here you can see a video of MPC optimizing for trajectories in configuration space while estimating the changing state of the world in real time. We've also been doing quite a lot of work in locomotion on difficult terrain. So here we're using a low-level MPC strategy for control of a quadruped. In this case, we're combining MPC with reinforcement learning, allowing the robot to contend with uneven terrain, loose rocks, and so on as it scrambles along the path. And then finally, we've been using MPC for the control of larger ground vehicles, like this skid steer Warthog that you see here, enabling it to robustly traverse muddy, wet terrain through dense vegetation, things like ice and snow, while all just using the same control strategy. So essentially, MPC and learning has allowed us to get these vehicles to traverse a wide variety of terrain. Okay, so you'll have noticed that like in each of these projects, we've used model predictive control as a key component of our strategy. We found that combining MPC and machine learning has been an extremely effective and I think underexplored strategy for decision-making and control for aggressive systems operating in complex environments. So let me describe MPC so that we're all on the same page here. So at each time step, we want to optimize for a horizon H trajectory in action space from our current state, ST. And usually this is formulated as minimizing future cost, subject to our current state, an approximate model of the system dynamics, and then hard or soft constraints defined in the state. So for example, if I have a ground vehicle, maybe these are like don't crash. We may also have constraints on actions like obeying joint or acceleration limits. And then we solve an optimization problem, and this could be through quadratic programming or stochastic optimization or something else, in order to get our plan. We then execute the first action, receive feedback from a state estimator, and then just return to the first step. So this is just kind of my high-level, hand-wavy model predictive control in a nutshell. Now, MPC is an extremely practical and pretty simple to implement algorithm, and has been used in a really wide range of control problems in industry. So just historically, it's been used in everything from food processing to automotive engineering, healthcare, and so on. And historically, when we think about MPC, it's often been used with fairly simple dynamics and the goal of driving a system to some set point or reference trajectory. But now, as compute has become much more available, and now that we have faster real-time simulators, we can actually solve all sorts of really complicated problems with nonlinear dynamics and really complex cost functions. And this is extremely useful for controlling fast dynamic robots in uncertain environments, as I'll show you. Now, I do want to highlight one thing at this point, which is just that in controls, MPC is often thought of as being really useful when there are constraints that must be obeyed. And so people will analyze feasibility and focus on the constraint satisfaction aspect of MPC. I have a bit of a different perspective on this, which comes out of my background in machine learning. And so usually when I think about things which are trying to choose optimal actions in some system, I just naturally think about reinforcement learning. And so I think about MPC as being particularly powerful and effective because of the approximate model that is used and the local optimization which is applied at every time step. So rather than trying to find a policy or a value function that works well everywhere in the environment, you can think about MPC as trying to find one which works well at my current location. And I'll return to this theme a bit later in the talk. All right, so while MPC is quite powerful on its own, I think it becomes really effective when we start to combine it with data collected while the robot's operating. And as we'll see, this will also provide a bridge between theoretically powerful machine learning strategies and the sort of real-world robotics tasks that we may care about. And so today, I'm just going to provide a sampling of 4 very different machine learning perspectives on MPC that our lab has worked on. And we're going to just start out with probably the most obvious way to combine machine learning and MPC, which is learning the predictive model from data. And I think about this as an example of learning inside of MPC because we're learning a component of the MPC algorithm. Okay. So to discuss learning within MPC, I want to consider the challenging task of aggressive off-road driving. So here is a robot. It's a high-speed off-road ground vehicle built in collaboration with several labs in computing and aerospace engineering at Georgia Tech. And our goal is to autonomously race this vehicle faster than a human can pilot it on dirt tracks. Now, some of you may have actually seen this project before, so I'm going to keep this section fairly short, but I think it's a good introduction to how we've used ML and MPC to control an aggressive robotic system. So just to give a very quick high-level overview, we have these robots that are basically 1/5 scale trucks. They weigh about 45 pounds, they're about 1 meter long, and they have top speeds in the 50 to 60 miles per hour range. They do all of their compute on board, and they use sensors including cameras, LiDAR, GPS, IMUs, and so on, in order to estimate the state of the vehicle. There are considerable computational resources on board these vehicles. So even though we were doing experiments with these maybe 5 years ago at this point, it still had an i7 processor, 640 core GPU, and was able to do quite a bit of onboard calculation. Okay, so we control the car with by modulating its steering angle and throttle. And the idea then again is we have this intelligent car, it's got perception, compute, we can control it. Now, how do we drive it at high speeds over rough terrain without crashing? So just to think about why this might be hard, I'm going to show you this slow motion video of the dynamics of the car as it's taking a turn at high speeds. So you can see that it's bouncing and sliding. Sometimes it has all 4 wheels off the ground. So the behavior is quite difficult to predict. And so this is actually a perfect candidate for MPC. So let me talk about the perception stack next, or sorry, the autonomy stack next. So there's several pieces to this. For the experiments I'm going to show you, perception just consists basically of state estimation with differential GPS and an IMU to get accurate outdoor position. We're estimating this with respect to a GPS survey of the environment. So we're just localizing the vehicle's attitude against this map. And then we're using model predictive control in order to generate actions. So let me tell you just a little bit about the model predictive control algorithm that we're using. So in the introduction to MPC earlier, I basically said that we want to optimize to find a good control sequence. But the question then is, how do we actually do this in practice? And there are many ways of doing this. And traditionally, MPC relies on convex optimization. But for complex tasks in robotics, we may want to use an approach that can handle non-convex costs and nonlinear dynamics. And one of the methods that we have found to work well for this is model predictive path integral control. So let me just discuss this a little bit. MPPI is a sampling-based approach. And the basic idea is that we first sample trajectories over a horizon H in the robot's action space from a multivariate Gaussian distribution with mean mu at time t. And then given the state and a simulator represented here by the model f hat, we apply the action sequence to generate a sequence of states. So for the autonomous vehicle, we're predicting different possible H-length state action trajectories that the vehicle could take. We then evaluate the cost of every trajectory. So for the vehicle, the costs are things like drive fast, stay near center of track, minimize acceleration. And then we compute a weighted average of the trajectories according to desirability, which gives us a smooth, low-cost trajectory. This can also be viewed as an update to the mean of the Gaussian that we originally used to sample our action sequences. Now, for those of you who are familiar with CMA-ES, this is actually a really, really similar approach. It's sort of a dynamic version of this. Okay, we then execute the first action of our new mean trajectory. We observe our new state, and then we return to step 1, shifting the mean by basically 1 time step. And so that gives us our new Gaussian distribution, which we sample from, and then we can continue the process. So you can see what this looks like for the racing task here in the lower right. So the red rectangle is the location of the vehicle on the track. And you can see that at each time step, it's rolling out almost 2,000 trajectories in simulation, indicating where the vehicle may be as it races around a track. And these are evaluated in order to determine cost. Okay, so this is the algorithm that we're going to use as a basis for a number of other pieces of the talk. So does anyone have any questions about this before I move on? I'm happy to take them right now.
It seems like no questions right now.
Great. So if there are no questions, I'll just move on.
I think there's one on the chat which came up. So where do you need to know the dynamics?
I'm sorry, say that one more time.
So a question came up on the chat. How well do you need to know the dynamics?
Oh, that's a great question. So the dynamics have to be modeled well in the sense that they have to be predictive. So I will talk about that next. How do you actually get a decent model of the dynamics which can control this at high speeds? So really good question. So before talking about that, I just want to mention that this approach is really, really fast. So sampling trajectories is a naturally parallel task, and it can be run in real time on a GPU. So for our robots, we can sample thousands of trajectories at about 50 hertz or higher. And all this is great because it means we can implement this fast version of MPC. But as the question suggested, all this is great, but like, how do you actually model the dynamics and like, how good do they need to be? So we could just use a simple kinematics model and hope that MPC with a low-level PID controller takes care of the rest. And this actually works really well for less aggressive driving, but for really high-speed driving, it would be nice to use something more accurate. So what we're going to suggest is using machine learning to estimate a function to approximate the dynamics. And to do this, we want to start with a good model class, so something which is expressive enough to capture the dynamics in the vehicle. So for example, we assume that the car is exhibiting general discrete time nonlinear dynamics. We then partition the state into its configuration and time derivatives, pretty standard in controls. And then we attempt to learn a fully connected neural network, which basically maps the current state in action to observed acceleration. And it turns out that this can work quite well. Now, an interesting question is, how do you actually learn a dynamics model like this? And it turns out that this is somewhat difficult, and it's not super easy to do this with just something like supervised learning. So let me just talk briefly about how you actually would do learning on a system like this so that the dynamics model is predictive for the tasks that we care about. So to learn the dynamics, we use an approach called DAGGER, and this goes back to old algorithm for DAGGER for system identification, 10 years old at this point, from Stefan Ross and Drew Bagnell. And we basically apply a iterative process where we first collect a distribution of data for each iteration and then solve a supervised learning problem over and over again. So the training for our dynamics proceeds like this. We basically first collect data from a human driving the autonomous vehicle. So the human drives the autonomous vehicle around the track multiple times until we get a good data set. We then collect new input-output pairs for learning this dynamics function. We add this to our existing data set. So in the first step, this is just empty. So we add our new set of data to that. And then we train the model using the data. We then take the trained model, and this is the sort of really important part, and we put it inside our model predictive control algorithm on the robot to generate a new data set. And then we repeat this process. So this allows us to incrementally build a data set that explores the state space encountered by our vehicle with the learned dynamics. And it just sort of does this well in practice, right? Like we're repeatedly collecting data in the area where the MPPI model or the MPPI algorithm with the trained model actually explores. And this results in a more robust dynamics model, which is ultimately more accurate and gives us a more resilient MPC algorithm. So let me just show you how this works with the real vehicle. So we're just going to start out by collecting data. Here is one of our students collecting data on the vehicle. And he's being a bit careful through the turns, obviously, because there's a bunch of slip there. And he just collects data of the car going around and around the track. Then we learn a dynamics model, we put it on inside of MPC and run it again. And we do this over and over again until we have a good dynamics model, which allows MPC to drive very aggressively around the track. And so through this bootstrapping procedure, we're actually able to ultimately drive the car faster than the human originally demonstrated. Now, one thing which is pretty interesting here, and we'll see it again as we as the video goes forward. Let me see if I can actually speed this up. If you actually look at how the car is driving here, as it comes around the near turn on the left, you'll see it actually turns outwards before turning inwards in order to take the turn at high speed. So this is actually something which is well known in racing. It's called the Scandinavian flick. And it allows you to essentially enter into this controlled drift around the turn. And this is something which has emerged through learning the dynamics model repeatedly in the interaction with MPC. Okay. This approach is also very robust because of the MPC algorithm. So the very fast updates here, you're going to see a rock hit the rear wheel of the vehicle, knocking it out of alignment, but the vehicle is actually able to recover and continue on. And then just in general, you can see the car as it's coming around these turns with all the bumping and sliding and basically flying through the air. It is able to do that over and over again without crashing. All right. So
Byron, maybe a quick
anyone have any quick questions about this? Yeah.
Yeah, I mean, these videos look super cool. So one thing I'm wondering is, how does the car know about the tracks? I mean, is the state space also including images by any chance, or?
Okay, so in this example, the vehicle basically is just looking at its position relative to a pre-computed track, and it's just using GPS and IMU. So here it is not using LiDAR or camera perception at all, like in these experiments. You'll see some experiments later where we are using the camera and LiDAR data.
Thanks. And there's another question on the chat, which kind of is asking how many dagger iterations are required to learn a good MPC model?
So in this case, basically what we're doing is collecting some mini batch of data in between like each iteration. So we'll run the car around the track a bunch of times, collect data, update the model, and then repeat that process. And I believe in this case, it's around 5 iterations of those batches of data. So it doesn't take a huge amount, like it doesn't take, a huge number of iterations in order to start achieving really good performance. Okay. So we started this section by saying we could potentially use machine learning to improve MPC, and we showed how we can learn a dynamics model to improve MPC performance. But in general, we can learn not just the dynamics model, but other components of the MPC algorithm. So the cost function, you can think about this as learning it from expert demonstration, or even how to optimize the model better. So think learning to learn. We can also treat MPC as a differentiable policy class and learn both the dynamics and cost function to hit some overall performance objective, as in like reinforcement learning or imitation learning. In my experience, this is actually a bit harder to get to work well in practice than using something like Dagger, which I just showed, but different people's mileage may vary. Okay, so now I want to switch gears and discuss how model predictive control itself can be viewed as a learning algorithm and how we can use this insight to build more effective MPC algorithms. All right, So the main idea is that we can view MPC through the lens of online learning. And here we're thinking about MPC as itself a learning algorithm. And it's basically optimizing the parameters of some policy pi at every time step. So let's just give a preview of how this works. So at each round of online learning, this corresponds to one time step. And at every time step, MPC can be viewed as a learner that chooses the parameters theta and then executes a policy with those parameters on the system. Next, we observe what happens. And in the context of online learning, we think of the system as an adversary that provides feedback to the learner by picking out a loss function that the policy will be evaluated on. The learner then uses the loss to update the policy so that it will perform better at the next time step. Now, by thinking about MPC as optimizing a policy, there's a natural inclination to think about how it relates to reinforcement learning. And here, this is a bit different. So rather than learning a single policy that works well everywhere in the environment, we're instead rapidly updating a really simple policy at every time step so that it will work well wherever it's going to be applied next. So let's look at the details of this. So on the left, we have the online learning paradigm. And on the right, we're going to specify choices for a problem. So first, for each round of online learning, this is going to correspond to a time step in the system. That is, the learner will pick a new policy for every time step. And then second, the policy will just be a simple open loop control distribution. So you can think about this as a distribution of trajectories of actions. So note that this policy is not conditioned on state at all. It's literally just a distribution of action sequences. And we can think of the statistics of the distribution, so for example, the mean or covariance of Gaussian, as the policy parameters. Okay, so we're also going to assume a simplified simulator that takes the current state of the system and control distribution as input and produces a distribution of states as output. So using such a simulator, we can integrate the state forward in time. And returning to our MPPI example, this is exactly what the MPPI rollouts are approximating. So the idea here is that given a state, we can evaluate the quality of the policy at that state by estimating its expected cost in simulation. So now let's look at the loss. So here on the right, this is the expected cost under the simulated state action distribution, starting from the current state that we think we're in, ST. So basically, by generating a state, the system selects the loss function for our policy at this time step. Okay, so then from the online learning perspective, the objective is to update the parameters to perform well in simulation at the next time step. So in other words, we want to update the parameters so that the policy will have low cost in simulation wherever the system decides to evaluate me next. So for example, the next state. To update the policy, we use a very general algorithm called dynamic mirror descent, which has two steps. So in the first step, it performs just regular mirror descent to update the control distribution so that it has lower loss, so that it performs better in simulation at the current state. Now, mirror descent works by building a convex global upper bound approximation of the objective using a gradient G, a step size lambda, and a Bregman divergence. And this could be like squared distance or KL divergence. And then minimizes the surrogate objective. So the gradient basically tells us what direction to take to improve our parameters, and the Bregman divergence just keeps me close to the previous solution. The result is then a updated control distribution that performs better in simulation for the current state ST. We then execute the first action from the updated control distribution. And then we move to the second step of dynamic mirror descent, which is the dynamic part. So this uses a predictive model to shift the distribution forward from time step t to time step t+1. And you can think about this as similar in some ways to like a state space model and a Kalman filter. So if this is accurate, we can expect to perform well on the next state. The online learning algorithm then moves to the next round, which uses the newly proposed open loop control distribution together with the next state. So just in summary, this dynamic mirror descent approach views model predictive control itself from the perspective of online learning. MPC can be viewed as applying dynamic mirror descent to rapidly adapt a really simple policy as we traverse our state space. Now, intuitively, if our simulator is accurate and we can predict the next state, then we should receive low regret.
Byron, can I ask a quick question over here?
Yeah.
So when you're saying the adversary selects the cost function, what does that exactly mean? Like, I mean, I was assuming the cost function.
Think about it as like, if the world is like the adversary, right? And I'm in simulation. Okay. At the next time, like I'm going to execute an action. And at the next time step, the world is going to put me somewhere in the simulator. Okay. So if I have like a dynamics model and simulation, I have some prediction of where I might end up, but the world might have different idea about that, right? Like if my dynamics model is not perfect, the world might put me somewhere else. So I think about that process as like the world is my adversary telling me where in simulation I have to like play next. Does that kind of make sense?
I see. Okay. Got it. Thank you.
Okay. So it's kind of a weird way of thinking about it, but I think it's actually like quite powerful. Like you're thinking about, like if your simulator is not good, then the world sort of can put you at a wider variety of places at the next time step, right? Like you're just not able to predict as well where you're going to end up. And like the better your simulator is, the less, you know, uncertainty there's going to be about like where you're going to be required to play next. Okay.
So maybe there's one more question on the chat, if it is okay.
Yeah.
So it's asking, you know, how long do the policies remain stable in open loop / what is the time horizon H, you know, that you have been, you know, showing on the slides?
Yeah, that's a really good question, and I'll address that a little bit in the next section, actually. So it depends on how accurate your simulator is. The other thing to note is that you know, your dynamics model doesn't necessarily have to be open loop, but that being said, you're still like, even if you're using some like controlled or some closed loop policy like inside of MPC, and this may be going beyond what we really should be talking about right now, but if you do if you generate closed loop rollouts, it's still going to be closed loop with respect to your simulator. So a lot depends on like how good the simulator is. So one way of thinking about this just in general is if your simulator is really good, you can get away with longer horizon rollouts. And if your simulator is bad, the longer horizon tells you less and less about what's going to happen in the future. And so in the next section, we'll talk a little bit about how to alleviate some issues around just having not great simulators and therefore not being able to use longer horizon rollouts. Okay. So the online learning framework, which I just described, provides a very clean derivation of many MPC algorithms, and you can think about them as special cases. And these include the receding horizon version of LQR, the cross entropy method for MPC, and MPPI. And in each case, we can choose a policy, pick an objective, and then just optimize with dynamic mirror descent. Now, here's the kind of like crazy part about all of this. If you actually look at the details, you can see that this optimization perspective on MPC algorithms actually shows that many of the off-the-shelf MPC algorithms are suboptimal from this viewpoint. So they make a number of heuristic choices which are not necessarily justified. And an example of this is step size, which is hidden in the usual stochastic MPC derivations, but a really important component of getting an optimization algorithm to work well in practice. The other thing is that this perspective also provides a prescriptive approach to MPC design, and we can easily generate new algorithms that make sense for a particular application by just choosing a particular policy per round loss, divergence, step size, and predictive model. So if we choose different ones, we can just get new MPC algorithms, which actually work pretty well. So just to explore the step size thing, because I think it's kind of cool. So using insights from this dynamic mirror descent, or DMD MPC, we're able to better tune optimization and generate new algorithms. An example of this is we can generate a new variation of MPPI that can reduce the number of samples needed for the dirt track racing scenario by almost 2 orders of magnitude. And this allows us to use much less compute and scale MPC to higher dimensional problems. So here we're just using 64 trajectories compared with 2000 trajectories by simply thinking about the step size variable and tuning it. Okay. Just a couple other things. So we've also used insights from DMD MPC to design better MPC algorithms for higher dimensional control problems, like the control of a manipulator. So here's an example from our STORM paper, which uses MPC as the core component of a system for fast reactive control. We've added a number of improvements to MPC here, including quasi-random sampling and covariance adaptation to make the optimization more efficient. But I just wanted to show you that it can be used for very different types of robots. It's also the foundation for control for our DARPA racer team. And so I can't resist telling you a little bit about this because it's super awesome. We've basically scaled up to full-size off-road vehicles. So the vehicle you see there is a 3,000-pound off-road vehicle that can drive, like up to something like 60 miles an hour. We're currently running these vehicles at Dirtfish, which is a rally school in the foothills of the Cascade Mountains, about 35 minutes away from UW here in Seattle. And then we also are running them on a ranch in Eastern Washington, about 170 acres of off-road test environment. Now, unfortunately, this is a DoD program and only some footage has been approved for public release. And I'm going to show you some of it just to give you some of the ideas of the types of terrain and problems we're tackling. So here is sort of a highlight video. You can take a look at this on our lab YouTube channel if you want to get the full experience. There may be a little 1983 Metallica playing in the background, so Motor Breath. For those of you who are older, maybe you're into metal. But what you can see here is our vehicles driving around on off-road terrain. They're generally going between 10 and 22 miles an hour and figuring out how to navigate extremely variegated terrain, including sometimes dense vegetation or really steep slopes. So this is driving on slopes which are up to 30-degree pitch and 20-degree roll. So pretty heavy duty slopes. Yeah, and then I guess the video is frozen even for me. So let me just move on to the next slide. But we drive it through like water, through ditches, through all sorts of crazy off-road terrain. All right. So let me just also show you a little bit about what's going on inside of the vehicle. So we talked a little bit earlier about perception. So here is an older version of our perception system. The new version hasn't been approved for public release yet, but trust me, it's super awesome. So essentially what we're doing here is fusing noisy semantic segmentation into a consistent representation of the environment. So in the lower right, you can see a cost map being aggregated over time. In the other videos, so in the front camera, rear camera segmentation, and LiDAR segmentation, you can see that we're segmenting the environment, and it's very noisy, but into a sort of easy, medium, hard, and lethal cost regions. And then all of that together is fused into the cost map in the lower right. And here you can see like MPPI being used in order to control the vehicle. through this environment at fairly high speed. So I think we're going almost 20 miles an hour here.
So out of curiosity, when you're doing the segmentation, I mean, is it based on like grass versus mud versus something else, or is this, I mean, what are the kind of categories?
Yeah, that's a great question. So basically, the semantic segmentation, which is going on underneath this and in our more advanced perception system, which I'm not showing, is effectively actually classifying the terrain into 30 different categories, which include basically trees, bushes, rocks, walls, mud, dirt, grass, and so on. So there's about 30 different categories. And then those categories here are mapped to different traversability classes. And then that's ultimately mapped to cost. And so in the lower right, the cyan is basically, and magenta is basically lethal, where purple is clear and the darker kind of red is higher cost. Does that make sense?
Yeah. I mean, I guess there's another question on the chat. How critical is it to fuse the rear camera segmentation into the cost map from a performance standpoint?
Yeah, so you're not seeing like the whole stack here. So basically, there's also a planner running like in the background, and when we get stuck, we need to be able to get the robot out. And so the planner will help the robot go through and execute, K-point turns in order to extract it from some situation and figure out how to get out of whatever situation it's in. So in that case, obviously being able to see behind you is fairly important. So LiDAR and camera can both help there. Here, what's actually happening in the video, there's a downed log in front of the robot, and there's a couple things going on, not least of which is, sort of found a way around it, but then there's a lot of steam coming off the front of the robot, which interferes with LiDAR in a kind of nasty way. But it speaks to some of the challenges of this problem. You can see that there's droplets of water and mud on the camera lenses. There's steam blowing around the LiDAR and so on. And so the perceptual challenges for this problem are significant. And there could be a whole other talk about sort of how to do perception for off-road driving, but that's not the focus today. Okay. So let me move on. All right, so I want to step back and take a third very different learning-based perspective on MPC. So MPC requires a number of choices for it to work well. So for example, the length of the horizon and the accuracy of the simulator, or even the number of samples used in sampling-based MPC methods. So this may speak a little bit to the previous question about horizon length. So for example, if our planning horizon is too short, then MPC is myopic and it fails. Like it literally cannot see far enough into the future to make a good decision. And here are two simple examples of that on a synthetic robotics problem to illustrate the types of failures this can cause. So on the left is a pushing task where the goal is to push the dark block to the red goal position. But in this case, due to the short horizon, the manipulator can't reason far enough to move around behind the block in order to get it to the goal. On the right is a cup and ball game where the object is to swing the ball up and catch it in the cup. And again, if the reward is sparse, you get reward when the ball is in the cup. Then a longer horizon is needed to discover regions of high reward. So in this case, the horizon is too short and the agent just sort of swings the ball around randomly. Now, one way to solve this problem is to just lengthen the horizon. But this could be computationally expensive or maybe too expensive for real-time optimization. It also requires us to simulate further and solve this harder problem. So methods like MPPI may need prohibitively many samples to converge to a good solution. So a different approach. We think about the connection between MPC and reinforcement learning. And we've already seen how MPC can be viewed as optimizing a policy. So for example, we saw that the current state robot can use an approximate dynamics model and cost function to optimize parameters of that policy, such as the multivariate Gaussian. But MPC can also be viewed as locally approximating the expected cost to go at a given state for many actions. So in other words, the Q function. So from a reinforcement learning perspective, we can view policy optimization as being accomplished by constructing a surrogate MDP, MHAT, with a simulated inaccurate dynamics model and a cost function and a finite horizon H. So MPC then forms a local estimate of the Q value as the expectation of the discounted cost over horizon H, followed by a terminal Q estimate or terminal cost in the surrogate MDP. Now, the definition of this Q function is given at the top of the slide here. Basically, it just says that we can write the Q function as the expected sum of discounted costs over horizon H, followed by the terminal Q estimate. The optimization step in MPC attempts to find the optimal policy parameters phi star to minimize the cost to go. And then we execute a single action from the policy, and the process is repeated from the next system state, resulting in this feedback controller. Now, the key to overcoming the challenge of a finite horizon without actually extending the horizon is to pack the expected cost to go into this terminal cost or Q function. And this is the basis of so-called infinite horizon MPC methods. So while running MPC, we can collect data and use reinforcement learning to be estimating a Q function for that terminal cost. And MPC will improve as we get better and better final Q estimates. Okay. So this can solve the problem of having too short a horizon, but what are other ways in which MPC can fail? So having an incorrect or biased simulator or dynamics model can be problematic in that the early part of the trajectory that you're predicting might be accurate, but as you sort of compound the inaccurate dynamics model with increasing horizon, the trajectories become less and less accurate. And so what we can do is we can simultaneously overcome model bias while increasing the effective horizon of MPC by blending in the learned value function at every step in the horizon. So a blended Q estimator constructs the H horizon estimate as an exponentially weighted average of all of the horizon estimates ranging from 0 to H using some parameter lambda. And this causes shorter range predictions to rely relatively more on the model from MPC and longer range predictions to rely relatively more on the estimated Q function. And then we can further see that by changing lambda, we can effectively tune the horizon length. So increasing or decreasing our dependency on the learned Q function. So for example, when lambda is equal to 0, the algorithm reduces to only using the learned Q function. We don't use the MPC model at all. Instead, we just optimize to find the best action given the Q function. And when lambda equals 1, we recover just the original MPC estimate with the Q function only used as the terminal cost. So for intermediate values, we can smoothly interpolate all horizon estimates, thus trading off the MPC algorithm against Q learning. And this leads to a powerful insight. We can implement MPC to control a robot. And we already know that this works pretty well. But as the robot operates in an environment, we can simultaneously be learning a Q function and slowly start to decay lambda as the Q function gets better. And this will potentially remove bias as we encounter more data, while also reducing variance when used with sampling-based MPC. And this is very similar in some sense to TD lambda. Okay, so we've completed a number of experiments in simulation showing that model predictive control blended with Q learning can overcome fairly severe model bias as the agent gains experience with a task. And we're currently working on implementing this approach to enable real systems to continuously improve over MPC as they naturally collect data while performing a task. All right, so We're running out of time, so I may just go through this section very briefly. The last thing that I wanted to talk about was this idea of learning a policy of model predictive controllers. So the idea here is rather than learning a policy that maps states to, for example, something like joint torques, we can choose an RL policy to choose different MPC controllers as actions. So just to motivate the approach, we've been working on scrambling over complex terrain with quadrupedal robots. And similar to off-road driving, this is difficult because of the complexity and dynamic nature of the terrain. It's also something which is fairly difficult to simulate accurately, especially if you're thinking about kind of kicking rocks or moving through brush. So instead, we use a hierarchical approach to policy design, where again, the lower levels are handled by MPC and the higher levels are learned in sim. So I'm gonna skip through this a little bit because I do want to get to some questions. But let's get to the overall approach. So basically, the overall idea here is that there's this low-level MPC controller. It's actually based on the MIT Cheetah 3 controller. And there are a number of gate parameters. And what we do is we learn a gate policy in simulation that learns to pick out the correct gate parameters. And then the low-level controller sort of handles everything else. And one of the insights here is that the low-level controller is really sort of overcoming the sim to real gap, right? So it does what controllers do well, which is it is rejecting disturbances and like differences between what I think might happen and what's actually happening on the system. The just overview here is that we're mapping a simplified state representation to 3 MPC parameters so that the policy can control gates. And then we train the policy in simulation with a very simple reward, which is just reward for staying alive, for being close to the speed that we're trying to track, and for being low energy. And the idea is that if we can learn a good, efficient gate for different speeds in simulation, then again, the controllers do what they do best. They handle these perturbations and this difference between sim and reality. Okay, so there are 2 huge benefits to this approach. So first, by abstracting the policy to a higher level, rather than directly controlling torques, we can train it really fast in simulation. So converges in about 2 hours. And then second, because the controller is very robust, we can get zero-shot transfer to the real robot. Furthermore, with that really simple cost function, which I showed on the previous slide, the approach automatically discovers efficient gates and smoothly interpolates between them. So we can generate a very efficient, energy efficient policy in this way. And just to kind of give some examples, when we're trying to walk at low speeds, the robot automatically discovers to move 1 leg at a time. If we move up to medium speeds, it starts to trot, and then at higher speeds, it starts to execute a fly trot. The approach is robust. So here you can see my student pushing the robot around with a vacuum during COVID at his house. And it's able to recover. And then again, we are able to actually drive the robot around on fairly long loops around campus. Basically, it's able to do almost a mile loop in about 40 minutes. And we have a zero-shot transfer to more complex domains, including the winter domain. So every once in a while, it actually snows in Seattle. And when it does, I usually try to get the robots outside. But here you can see it's working just fine in the snow. All right, so let me just summarize now. So we explored MPC as a powerful paradigm for controlling robots in uncertain dynamic environments. We looked at how MPC could be combined with machine learning in several different ways, using machine learning to learn models of robot dynamics, showing that MPC itself could be interpreted as an online learning algorithm, and through the insight, tune for better performance. And then finally, we covered 2 different ways of combining MPC and reinforcement learning. And I think we've only really started to scratch the surface here. So there are many different possible ways of combining data and model predictive control. And I think, again, it's just a really powerful way to integrate learning, real-time simulation, and control on autonomous systems. So to conclude, I want to thank the PhD students who have worked with on projects at the intersection of machine learning and model predictive control, and whose work led to many of the insights that I discussed today. Thank you.
Thanks, Byron, for the wonderful talk. So we have time for maybe 1 or 2 questions. So maybe I'll start with 1 question. So in one of the sections you mentioned about, you're estimating the Q function, and then as the Q function becomes better, you trust the Q function more. So I'm curious, what do you use as a metric for knowing when the Q function is good?
Yeah, that's a really good question. And in this case, we are not doing this in like a smart and maybe like appropriate way. So essentially what we're doing is we just have a schedule. So we just say, as we collect more data, we start to reduce lambda. But what you should be doing is actually trying to also estimate your uncertainty in the Q function at different states, something like this. And then you might be able to do like fairly clever things like decide when you want to rely more on your simulator, like let's say in areas where you have not collected a lot of data, and where you might want to use the Q function, which might be in areas where you have collected a lot of data. And so I think there's a lot of room to improve and do things properly. So the main insight is just that you can trade these off, and that can result in pretty powerful approaches which correct for errors, both in the Q function initially or in MPC with like a bias model as you get more data.
Great, thank you.
May I ask a question? May I ask a question, please?
Yeah.
Can your method be applied to 2-dimensional pattern recognition or 3-dimensional object recognition, please?
So I think for most of the reinforcement learning methods, we're focused on problems related to selecting actions. So in general, you can think about like 2-dimensional pattern recognition or 3-dimensional object recognition as a supervised learning problem. So it's a bit of a different thing. So you use other tools to solve those problems.
Thank you very much. Thank you.
Thanks.